Hi there, my name is Stefanie Kaboth-Bahr. I'm a postdoc at the University of Potsdam in the working group of Martin Trout. This is an introduction video to a publication that, together with a lot of colleagues from various institutes, we've got published this year in PNAS that deals with climatic changes in Africa and how these might relate to human evolution. The reason I'm making an introduction video for this particular paper is that Will Gosling and I started thinking about the Mapping of Africa project that was funded by the INCWA based on this particular paper, and that the ideas presented in this paper are one of the things we would really like to discuss with everybody who's interested in terms of how does this process work in detail, how can we apply the concepts proposed in the paper to different time scales, to different time phases, and how can we better tie climatic changes across Africa to human evolution in general. So I'm gonna basically go through the study really quickly so you just can get an overview, and we will make sure to have the publication also online available for you in case you don't have a subscription to PNAS. So first off, let me start with basically the background of the study. I'm pretty sure you have seen a figure like this before in various publications. It's in a way an attempt to link climatic aspects or changes to human evolution in this graph going from left to right. There are very different ideas about how climatic change actually influenced human evolution, with different hypotheses shifting from time to time. One, like in the beginning, the idea was that perhaps dry periods could be a driver for evolutionary steps. Then it shifted towards more wet period being, or wetter periods being essential for human evolution. For a process point of view, it has been argued that insolation is a driver for climatic change in Africa, but particularly on timescales of human evolution, that processes like global ice volume changes, CO2 changes are fundamental processes that drive climate change in Africa. However, as you can see in this figure, the linking up climate changes or processes that drive climate changes, for instance, the eccentricity axis that you see on the left, which is a representation of insolation changes, or the global climate transitions that you can see marked as green bars, like indicating major transitions in global ice volume change throughout the last 5 million years. It's not so easy to align these aspects to the evolutionary tree you see on the right. So this paper that I'm presenting was trying to look at this from a different point of view, trying to find a new way on how to assess climatic change, and then try to bridge the gap into how these climatic change actually translate to human evolution. So from a get-go, we try to do this a little bit differently, because a lot of the studies you find out there are usually linked to one site at a particular location within Africa. So what we try to achieve with our study is that instead of looking at one region or one core, we try to, in a way, summarize everything that's available for a certain time period, and then look at Africa as a whole rather than in pieces. So what we did is, you can see this on the left, we used marine records and terrestrial records and combined these. So just for an orientation, these sites that are marked with tiny small gray dots reference the original site location, in this case in the Mediterranean Sea, and then the big gray dot is a projection on the land of what it represents. So in case of MED, which stands for Mediterranean, this is an actually marine record that traces Nile River discharge. The same goes for SAH, so it stands for Sahara. This is a dust record. And another one would be the one from the Congo River Delta that traces Congo River outflow. What we also have are the ones that marked in black. These are terrestrial records from Lake Bodoumtwi Kaboth-Bahr, Lake Magadi, and Lake Malawi. So this is an entire range of records that cover within reason the last 600,000 years of African climate change from different aspects of the continent. So we picked the proxy records from these sites that actually translates into wet-dry proxies that had an age model that is more or less comparable to each other, and that we assumed that they all have a common driving mechanism. So whether or not it's glacial or interglacial change, or whether or not it's CO2 or insolation, that all of Africa should change one way or the other because the process affects all regions, not just one. So what we're trying to do is do a big picture analysis rather than looking at individual records and individual variability that was captured in these sediment records. With this being said, was a question of how can you, because these are very different proxy records, how can you put them together and then extract one signal out of this? So what we basically did is we made a PCA. So we collected all the data sets from all these sites and then run a PCA over this entire data set. The PCA then basically selects the one signal all of these sites have in common, like the one thing that represents the best all of these records. So it's a very simple method, and of course from a statistical point of view there's a lot more to it than what I just explained, but in a general way it's a fairly straightforward way to get a signal out of a whole bunch of individual signals that you then can compress into one, and this one signal you can then go and try to interpret it. So this is pretty much what we did. So we collected all of these sites, 11 records in total, and then run a PCA on that. The result of that PCA you can see here. On the bottom you can see age from 0 on the left to 600,000 years ago on the right, and then you see the PCA axis which goes from +4 to -4. What you can see here is a lot of wiggle waggle, which at the moment isn't really showing much of anything. However, when we look at this record more closely, this combined signal of all of Africa that's available at the moment through proxy records, we notice something that is not necessarily as obvious in the individual record. And that is simply that it looks a lot like an insolation signal, especially the eccentricity signal over the same time period. This is something, if you look at some of the individual records, is not necessarily easy to capture, but if you look at the African signal as a whole, you can actually see this. And this similarity feeds into the general idea that insolation changes are a main driver of African climate change. So when we looked at this PCA result, we also were thinking about what do the orientation of the sites within the PCA mean? So, because if you run a PCA, the first principal component, which is the PC, also explains most of the variation, so the most is, so to say, the most dominant signal, but it also tells you something about which component of the signals you put in is related in what relationship to the others. The interesting aspect when we run the PCA is that all the Eastern African sites, like the Mediterranean record, Kaboth-Bahr in Ethiopia, Lake Magadi, and to some extent also Lake Malawi, they all orientate to one side of this PC, whereas all the Western African sites and Southern African sites orientate to the other. So, which if you translate this means everything on the plus side is East African, and everything on the minus side of this is West Africa. So you have a clear distinction, a geographical orientation of these sites relative to each other. They do not react the same, they're basically in an opposing pattern to each other. The way we looked at this was that this could mean only one thing, that whenever East Africa was becoming dominantly wet, West Africa was becoming dominantly dry, and vice versa. So you have a very distinct east-west gradient across the African continent. This in a way is very interesting because you're usually not used to, in the climate variability assessment of Africa, you're usually not used to this kind of argument that there is an east-west gradient. What we also noticed is that, as you can here now see with the nomenclature of phases, there are very distinct phases within the last 600 years that, for instance, through a breaking point analysis, you can truly assess and confine. So just for you to get an idea what it means when I say it's shifting, the moisture center across Africa shifts from east to west, I'm going to concentrate now on the middle part of our results, like the change from phase 2 to phase 3, just to give you a visual of what we mean when we say you have a moisture gradient that shifts east-west. So this is a panel you just saw, and I just emphasized phase 2 to phase 3. So you have a wet Western Africa to shifting to a wet Eastern Africa. And what that means you can see on the right side now. These are the core positions on land, as well as the terrestrial record marked. The blue means they turn wet, and the red color means they're dry. How did we assess this? That's simple. We used the time span that was confined by the breaking point analysis of the PC1, and then run a medium analysis over the proxy record. So assessing for each individual site over this time period is the median value of this time period is below or above the average over the entire record. Since all of these records indicate wet-dry conditions, this gives us an idea when a specific site shifts either to dry or to wet conditions relative to that site. So this is basically what you can see here in these two panels, one representing phase 2, which is the upper one, and one representing phase 3 is the lower one. And what you can see when you go from phase 2 into phase 3, that the Eastern African sites signaling drier conditions, with the exception of Lake Malawi, whereas the Western and Southern African sites signaling wet conditions. And then when you shift from phase 2 into phase 3, you can see again it switches around with West Africa, all the sites signaling dry conditions at that site, and Eastern Africa becoming wet. So this is a very clear east-west gradient that we can see and that we were able to assess using a PCA. The really interesting aspect now in terms of what does it mean of a process, you can see here in this panel. On the left side you see something you probably have seen a bunch of times in different publications, which is the annual migration of the monsoonous row, or the ITZ, across Africa. So this is the seasonality of where wetness goes, shifting from summer, where it is located more in the north, to a southern position during winter, boreal winter. So this is something that to some extent has always been used in paleoclimatic studies of Africa, trying to use this modern concept into translating it into change reconstructed from the proxy record. So you have a north-south shift. As you have today, you also have, it was also argued during, let's say, glacial interglacial periods, where during the warmer periods you would have a more northernward position of the monsoonous row, and during glacial periods you would have more a southern position of the monsoonous row. So this concept has been applied a lot. However, what's interesting is that this concept does not fit with what we found based on our analysis, since we have a very clear east-west gradient, not a north-south gradient, as you would expect it to be if this is simply a shift in the monsoonous row over time. So we were going through the different aspects of African climate, and one aspect of African climate that, particularly in paleo studies, has thus far not gathered so much attention is the Walker circulation. The Walker circulation is something extremely interesting, but really hard to grasp. The Walker circulation is a band of convection cells along the equator. It affects the entire tropics and to a very huge extent also the subtropics. And this is one of the major drivers for moisture distribution in the tropics. That includes, of course, Africa. But it's really hard to grasp. But water circulation changes is something that most of you have already heard of, one version or the other. And that has something to do with the fact that water circulation changes today is something you can see every so often when El Nino or La Nina comes to town. Because El Nino and La Nina today, as weather phenomena, are nothing more than a visualization of changes within the water circulation. I'll come to the process in a minute. I'll just try to make an argument why we think that's where the discussion needs to go. What you see here on the left are 120 years of observation data analyzed in terms of how precipitation relates to El Nino and La Nina variability. So this is based on observational data, not on proxy reconstructions. What you can see here is blue are humid and in red are arid, so dry conditions suggesting like the lack of precipitation. In the upper panel you've got modern La Nina conditions, and in the lower panel you've got modern El Nino conditions, and how this translates to precipitation changes in Africa. So La Nina conditions pretty much lead to a precipitation deficit in southern Africa in particular, but also along the west coast, while you have sorry, that was exactly the other way around. So La Nina conditions lead to more humid conditions in southern Africa and along the west coast, whereas eastern Africa becomes very dry, and vice versa during El Nino conditions. So this is something that is fairly known. And if you look at these two panels, you can see that this fits much better to what we analyze from the proxy records. So this particularly east-west pattern that we saw in the proxy records fits fairly nicely to these modern observational data. This got us thinking that perhaps El Nino, La Nina changes, so changes in the water circulation, are the process that underlines a lot of the African climate change on timescales of hundreds of thousands of years. Now going back to what that truly means, the water circulation, as I said, is this convection band along the equator. And in its neutral form, you basically have a lot of convection over, let's say, the Indonesian Pacific realm, and then some South American, and then to some extent East African. During, let's say, El Nino conditions, this is emphasized because the convection cells actually shift, and they shift east-west along the equator. So in El Nino, so a warming of the Pacific Ocean would lead to convection moving away from the Indonesian realm to the part of the Pacific that is towards South America, and it would also emphasize precipitation over East Africa. La Nina conditions do exactly the opposite. So these east-west changes are very distinct, linked to changes in the water circulation, which today is best explained by using El Nino and La Nina conditions, since they're manifestations of the water circulation. So that's really got us thinking, if that is the case, then we actually do have a tool to reconstruct Paleo-ENSO variability by using sea surface temperature records here from the Pacific sides, and look at the gradient between both to see if you can reconstruct past El Nino-like, La Nina-like conditions over long periods of time. And that's what we did. What you can see here in black with its axis on the left is the PC1 record you've seen before. So this is a Pan-African climate signal over time, again from 0 to 600,000 years ago. And in red, with its axis on the right, you can see the SST gradient across the Pacific that I just spoke of. And what you can also see, and that we emphasized in the study, is that these two records fit fairly nicely, much better than we would have expected them to be. There are some offsets here, particularly in the older part. But that might also relate to the partially huge age uncertainties from the Pan-African records, which generally are fairly good with age constraints over the last 300,000 years, and then particularly the terrestrial records, which make roughly half of all the records used for the PCA analysis. The age constraint getting worse after 300,000 towards the end of the record. But the general pattern between the Pan-African signal and the PaleoENSO signal, here shown in red, is fairly nice. So that gave us some idea that PaleoENSO variability, so Walker circulation changes, are at the heart of long-term climatic changes in Africa, which is something that has not been considered as much as it perhaps should. It is also a way using the Walker circulation to retranslate how an insolation signal can translate into a climate signal in Africa itself, because insolation changes have been argued for a very long time. There has been already studies from the 80s from several authors that already argue insolation being a very important part of African climate change, but so far a mechanism was missing that translated this insolation change into African climate change. And this study tries to fill this gap by proposing that PaleoENSO variability is a way on how to process this and a way on how to assess climatic change in Africa. So to simply conclude the main points of the paper and give a little bit of an outlook on what we like to discuss, particularly in terms of the Mapping of Africa project, is we argue in the paper that moisture availability in Africa was to a huge extent related to PaleoENSO variability, so an insolation-driven process. We also say and argue in the paper that the climatic framework fits fairly well with patterns of vegetational change and mammal distribution across Africa during the same time period. Because it's fairly interesting if you look into DNA studies or fossil record studies of mammals, that mammal population changes and distribution in Africa follows a very similar beat than the phases we confined based on our PaleoENSO signal. So one of the major changes in a lot of mammals, for instance lions and giraffes, is around 300,000 years, which is a transition we find again in vegetational changes and again in human evolutionary records and again in climatic changes. So there's a lot of alignment that exists between the climatic framework we're proposing and vegetation change, mammal distribution and population changes, and to some extent the fossil records of humans. This kind of gets us to the outlook part, because if you take the idea that PaleoENSO is a main driver of climatic variability in Africa, you have to consider a couple of aspects. First off, the Walker circulation that you need as a process to do all of this is actually not that very old. The way we understand Walker circulation today, it's maybe roughly 1 million years at most. Before that, the Walker circulation looked very different from today, since it is sensitive to tectonic changes as well as to changes in ice volume and so on and so forth. So for the last 1 million years, however, we can be fairly sure that the Walker circulation was more or less what it is today. If you use this assumption and then also assume that during this time period, African climate was very susceptible to this change in Walker circulation, this gets us to basically this figure. This is the PaleoENSO proxy based on sea surface temperature records from the Pacific for the last 1 million years. And then above you can see the insolation parameters, precession and eccentricity plotted. What is interesting is that the change at 300,000 years roughly that we already saw in our study published in PNAS is in fact the most profound climatic transition of the last 1 million years, because it switches from a dominantly wet Western Africa to a dominantly wet Eastern Africa. It's a fairly profound transition, and particularly the last 300,000 years is when, from a climatic point of view, Africa was really whipped into the shape and form that we see today. So particularly the long-term aspect of this new climatic framework we're proposing is one of the aspects we like to discuss within the Mapping of Africa project. Another aspect is, how does this process work on shorter timescales? So what we're looking for right now is the timescales of hundreds of thousands of years and the 400 kiloyear cycle of eccentricity in particular. But the question is, how does this process work on anything shorter than that? Let's say 20,000 years, for instance. All of these are questions that we at the moment do not have answers to, and that we would really like to discuss. So I hope I could give a little bit of an overview over the study and the questions we're trying to answer with it, as well as the open questions we still have. Thank you very much.